As we start getting access to data, as we start using more and more sophisticated machine learning applications to analyze the data, we still have to think about what those analyses mean. We still have to think whether they make sense, and we have to visualize them and understand whether the complex statistical relationships or the cross-matching that you heard about in the last lecture is actually working. Right? And so what we're going to do is we're going to go through a series of machine learning techniques that you can apply to high-dimensional data. So that means that if you take the LSST data stream and you have 1,000 observations of the same point or same object on the sky over 10 years, we'll talk about how do we actually analyze those data. And then in the hands-on session, what we'll do is we'll go through everything that we've demonstrated or shown in this lecture. We'll go through using the AstroML code and using the Python applications, and we'll walk through generating those images. Okay? So we'll step through how do we actually do this analysis. And then on Friday, we'll move on to time domain and how do we analyze time series data. So one of the questions at the end of the last lecture was, what book should I read if I want to know about Bayesian analyses, if I want to know about machine learning techniques? And here are the books that I read, and scikit-learn I'll talk about in a second. If you want an introduction to Bayesian analysis, there's this really beautiful tutorial that's given by Sivia. It is an almost unique book in the sense that it is, for a textbook, it is extremely well written. The prose of it is beautiful. It's extremely clear. It's a wonderful, and it's very compact. It's a couple of hundred pages or so. It's a very compact introduction to data analysis from a Bayesian framework. What book do I use most of the time? I always go back to, if we're not actually reading the book, the AstroML book, I always go back to Hasti's Elements of Statistical Learning. It is basically a compilation of statistical techniques that you can apply to data. What's really nice about it is each one of the statistical techniques is in a very short and compact form. He provides figures for all of it, which demonstrates how the techniques work. So it's a very nice introduction to a wide variety of techniques. So you can just flick through the book and you can to try and understand what sort of data analysis you want to do. It's mainly written for R. So their examples and the code that they've made available is all uses R as opposed to Python. Machine learning, there's a nice book by Christopher Bishop from, I think it was Microsoft, on pattern recognition and machine learning from a Bayesian framework. That gives you a very good theoretical introduction to Bayesian analyses. And then in terms of actually applications, and we'll go through all of this in the hands-on session when we use scikit-learn. Scikit-learn has effectively, it's probably about 70 to 80% of the techniques that you find in statistical learning. Right? So it's very easy to come up with an analysis that you want to do, look up scikit-learn, and very easy to implement that analysis. Okay. So what analyses do we want to be able to do? So if you take a data set such as the data from LSST, what do we actually have? We have a series of observations on the sky. So this shows you two exposures. If we match those two exposures, as we talked about briefly in the first lecture, we subtract them, we can find the difference image. The difference image in this case is showing you a moving source, an asteroid moving across the sky. If we look at deep images, then what we might want to be able to do is to identify low surface brightness features, and these are stellar streams around this galaxy. And so what techniques do we want, what kind of astronomical applications do we want to do? Well, we might want to find the unusual objects, finding transient events, supernovae, gamma ray bursts. We might want to look for moving sources, asteroids moving across the sky, characterize their orbits. We might want to map out the density distributions for stars in terms to understand where these tidal streams are and what they're saying about the kind of underlying dark matter halo for this galaxy and its merger history. Or we might want to undertake the standard cosmological applications such as weak lensing, gravitational distortion of galaxies, and to understand through some sort of weak lensing tomography to understand the mass distribution as a function of redshift. Each one of these techniques, finding the unusual, finding moving sources, mapping out the Milky Way, dark energy, dark matter, weak lensing, baryon acoustic oscillations, you can rewrite those in machine learning, in a machine learning language. And if we do that, then finding the unusual becomes anomaly detection. Looking for techniques that you might use to find anomalies involves dimensionality reduction, and that's what we're going to focus on in this lecture. Tracking and finding moving sources is tracking algorithms and Kalman filters. The same algorithms that you use for finding asteroids, the machine learning community uses for tracking missiles across the sky. There are slight differences. Asteroids don't actively try to avoid being tracked, and so they don't actually change 90 degrees. On the other hand, there are about 10 million main belt asteroids, and if you had 10 million missiles coming towards you, the kind of accuracy of your ability to track them might not be one of your major considerations at the time. Right. Mapping the Milky Way, looking for low surface brightness streams is exactly the same thing as density estimation. You're trying to understand what's the density of stars as a function of position on the sky. If I want to characterize the distribution of those stars, I may want to undertake clustering algorithms such as endpoint correlation functions that Tomas talked about. And then gravitation, dark matter, dark energy, gravitational weak lensing, distortion of images. A lot of that comes in the computer vision techniques for how to actually characterize the shapes of galaxies. And then with many of the techniques that we use, the classifier that we have is often quite weak. And so you have to combine multiple classifiers to come up with a better classification strategy. And examples such as this are, which again, Tomas talked about a little bit, things such as random forests. And these techniques apply outside of the astronomical community, the Netflix challenge. Does anyone here know about Netflix challenge? Who doesn't know about the Netflix challenge? Okay, most of you. Netflix is a system, or it is a company that either sends you DVDs or allows you to stream video content. So one of the nice things about Netflix was that after a while, after you selected your 10 DVDs, first 10 DVDs, and you rated how much you liked them, what they would do is they would go out and make predictions about what movie you're going to like next. Right? And they'd use that based on all of the kind of historical user information that if you like these sets of movies, people who like those sets of movies also like this one. And their recommendations were pretty good. And so the Netflix challenge was a challenge that was created a few years ago where they said, we will give you a set of data to train off. You come up with a better algorithm than us, and we'll give you $1 million. It was a great thing for Netflix because many people tried this, and they tried many different techniques, and they got close to what Netflix was able to do because they give them a training set, and then they keep their blind test set, and they'd evaluate it later on. And so they were performing close to what Netflix was doing, but no one technique was working perfectly. Yeah. Yes, but so what happened was there was no one analysis technique that was working better than Netflix. But eventually the teams came together and realized that if you combine all of them, each one of those analyses is like a classifier, a weak classifier, gives you some evidence for what's going on. If you combine all of them together, you actually get a better estimate of or better prediction than any one individual classifier. And when they did that, that's when they actually won the Netflix challenge, and they won their $1 million. So, but the point behind this is that it was the combination of these classifiers that actually helped. Right? And so these are techniques that are beginning to take off in astronomy today. So what makes it difficult? Well, we've heard a lot about the data volume, but one of the real challenges that you face is the complexity of the data model, or the complexity of the data. You have complex data streams. we have, say, 100 petabytes of data coming out of LSST. It's noisy, it's incomplete, it has defects in it. We have to deal with all of that. We've heard about the complexity of the models for the universe, that they are not necessarily representative of the observations that we see, because we don't understand all of the physics that goes into the simulations, particularly below the kind of subgrid level. And then we have the complexity of the scaling of the types of science that we want to do. If you just take naive applications, then a lot of the techniques that we work with scale as n squared or n cubed. You increase the data volumes by a factor of 1,000, then that becomes a problem for you. So how do we deal with this? Well, the first thing we have to recognize is there are no black boxes. You can't just take an algorithm, whether it's from scikit-learn or off any other website, and download it, apply it to your data, and expect it to work. You have to think about what comes out of the data. You have to think about what comes out of the analysis, and you actually have to work with these analyses. I think there's only a couple of techniques in the last 15 years that I think that really work just straight out of the out of the box. One of them was neural networks. Another one was principal component analysis. But in general, you have to understand the selection of your data. You have to understand the uncertainties and the outliers within your data before you apply the analysis. Right. So those are all the caveats. So what techniques can we use? So I said we're going to talk about dimensionality and dimensionality reduction. One of the real difficulties is that as you increase the volume of the data, or the dimensionality of the data, what happens is that as you increase the dimensionality, the distribution of the points becomes much sparser. So there's two aspects to that. One is large dimensionality is hard to search through. And the second thing is if the data becomes sparse as you increase the dimensionality, then what happens is you need larger and larger data sets to train off. Right? So even if you've got your 100 million data points in your data sample, it may not be enough to actually populate the full high-dimensional space. Well, if we look at this figure actually goes back to, 1995. If you look at the distribution of data in just a simple three-dimensional space, so this is photometric magnitudes for a sample of I guess it was high redshift galaxies at the time, which means it went out to redshift of about 0.5. And this is U, B, and R. The colors of the points correspond to or correlate with the redshift. Red corresponds to redshift of 0.5, blue corresponds to redshift of 0. What you immediately see is that the data are tightly correlated within that space. They don't occupy the full distribution of space or available parameter space. They only occupy about 5% of the parameter space. The second thing you see is that within these data, there are physical correlations. Right? So the high redshift galaxies tend to reside over here, low redshift reside down here. If we look at these in different projections, you can actually see the data themselves are almost planar. It's a three-dimensional space, but the data occupy like a two-dimensional plane. And within that plane, the actual redshift and the luminosity of the data are actually correlated. So the question that we try to address is, how do we take this high-dimensional data, how do we project it down onto a lower-dimensional space such that those lower dimensions, that lower or the smaller set of dimensions actually correlate with the physics, right? So they correlate with redshift, correlate with luminosity. So we can take this to, that was only 3 dimensions, so let's take this to a higher dimensional set. I don't have a sample of data with 1,000 observations that we'll get from LSST, but a nice proxy for this is a spectrum. So you can ask the question, well, how is a spectrum like a high dimensional data set? Well, a simple way of thinking about that is if we just think in 3 dimensions, so we have a nice 3-dimensional distribution, and I take a point within those 3 dimensions, this is equivalent to a spectrum with 3 elements. So each one of these elements corresponds to an axis, x, y, and z, okay? And the distance along that axis corresponds to the amplitude of the flux. So there is a direct mapping between having a spectrum that may have 4,000 elements, and a spectrum can be thought of either a spectrum with 4,000 elements or a point within a 4,000 dimensional space. And that's important because when I talk about dimensionality reduction for spectra, it applies to scatterplot data, and it applies to images as well, and it applies to hyperdimensional spectral or spectral images, high-dimensional image cubes or data cubes. Right? So these techniques apply across all of these. So what do I want to do? Well, here's a set of spectra from, this is a Sloan Digital Sky Survey, going from elliptical galaxies through to highly rapidly star-forming galaxies. You can see that there's a kind of a smooth transition from one to the other. Even though there's 4,000 elements within this spectrum, there's a smooth transition from an elliptical galaxy through to the star-forming galaxy, or through to the passive evolving galaxy and through to the star-forming galaxy. So what's happening is the continuum is going from the red to the blue, so there's kind of a tilting in the actual continuum, and as I go from ellipticals down to star-forming galaxies, then I progressively increase the number of, the amount from the emission lines. Okay. So you might say, well, that seems like there's a very smooth transition, so maybe I can describe these data with a smaller number of components. So the question becomes, if I have a set of functions or basis functions or eigencomponents, as we'll talk about them, can I describe each one of these spectra just as a linear sum of components? And if I can do that, how do I actually estimate what those components are? So the first thing you can do is to work with principal component analysis, which probably a large fraction of you have come across. Let's think about this simply in a two-dimensional space. So we have a set of scatter points, scatter plot, and their axes, which are x and y. We can immediately see that the data are actually correlated both with x and y. So if I wanted to decorrelate these data, if I wanted to choose a new set of axes or a new set of components, how would I choose those components given this distribution of points? And if I wanted to do this in a linear way, so I would just rotate those axes, what would I actually do? Well, clearly what you would see is you want to align this axis along the scatter, right? Along this direction here. And that would give me my first principal component. What am I actually doing here? What I'm actually doing is I'm aligning the first or principal axis along the direction of the maximum variance. Another way of saying that is I'm aligning it along the direction where I am minimizing the orthogonal distance from this line to each one of these individual points. Okay? And that's what principal component analysis is doing. First thing it does is it chooses the direction that corresponds to the maximum variance within the data. Then it chooses the next direction that's orthogonal to the first principal component that maximizes the remaining variance. Right? In a mathematical sense, you can just think about it in terms of the correlation function. So we'll think about all of our data as being centered, which means we've subtracted off the mean, which you can see we've done here, so that it's all centered on x equals 0, y equals 0. We can calculate the covariance matrix for the data. And as you would expect from these data here, if I just did the covariance matrix for x and y, then I will get off-diagonal components because the data are actually correlated in x and y. What I want to do is to define a new set of bases, and those bases should be uncorrelated with the data. And that means what I effectively want is a correlation matrix that has non-zero for the off-diagonal elements. So what I'm looking for is a transform of x that will take me from the correlation or covariance matrix to a correlation or covariance matrix that has zeros for the off-diagonal elements. And if you just run through, if I just put that transform on against x and I ran through, I just propagate it through here and then substitute in for y, you'll see that all you're really trying to do is to take the covariance matrix, multiply by the transform of this operator on x, times the new covariance matrix, which is a diagonal covariance matrix, again times the transform. And this is just really the definition of an eigensystem. Okay. So all that's really saying is that if I can do an eigenbasis analysis on the covariance matrix, or as I'll show you in a minute, if I can do a single value decomposition on the covariance matrix, I'm going to get out a set of eigenfunctions. And we'll see what that means in a second. So how do you do this? The simple way to do this is with single value decomposition. This just says that if I take any matrix, I can describe it by a set of eigenvectors. These are the left eigenvectors, multiplied by a diagonal matrix, which correspond to the eigenvalues, multiplied by the right eigenvectors. So if I transform this, I just substitute in x into this relationship here, then you can see that x transpose times x just equals v times sigma times u transpose times u times sigma times v transpose. And if I simplify that, I get v times sigma squared transpose times v times sigma squared times v transpose. So these are the right eigenvectors. This is the equivalent to the covariance matrix that we have here, and these are the transpose of the eigenvectors. So all that says is that if I do single value decomposition, the fact that this relationship here looks exactly like this just means if I do single value decomposition on the covariance matrix, then I get out a set of eigenvectors. So that's why we use SVD for a lot of the principal component analysis. One quick note on speed is you can calculate the covariance or the correlation matrix. So what do I mean by that? Well, if I take a vector, say I take a matrix of spectra. So each one of these is a spectral element, and in the going down on the rows is the number of spectra that I'm working with. I can build up the covariance matrix by taking x times x transpose, or I could build up the correlation matrix by taking x transpose times x. And I may have got that back to front. Why is that important? Well, if I take x times x transpose, what I'm going to do is I'm going to take this row and then multiply it by this column. And that means that the resulting covariance matrix is going to be the number of rows by the number of rows. If I do it as a correlation matrix, I will take this row, I'll take it here, this row here, and multiply it by this one here, and that means it will be the number of elements in the spectrum by the number of elements. Right? So you can produce a covariance matrix which will be the number of elements by the number of elements, or you can produce the correlation matrix, which is the number of spectra by the number of spectra. Okay? Single value decomposition scales as effectively as an n-cubed operation. So what you want to use is whether you use the covariance or the correlation matrix, you end up with the same sets of eigenvectors. So the importance is to work with the projection that gives you the smallest number of dimensions. So all I'm really saying there is if you have 1,000 spectra and each spectrum has 100,000 wavelength elements, I can build up the correlation matrix will be 100,000 by 100,000 matrix that I want to apply an SVD to, or I can calculate the covariance matrix, which would be I think I'm getting this back to front. So if I have 100,000 element spectrum and I have 100 spectra, I can build up the correlation matrix, which would be 100 by 100, or I can build up the covariance matrix, which would be 100,000 by 100,000. Single value decomposition on each one of those matrices. If it scales as n cubed, where n is the dimension of that matrix, then clearly I want to work on the 100 by 100 matrix and not the 100,000 by 100,000. Right? So determining how you project how you generate either the covariance or the correlation matrix is important from the computational side of things. In reality, when you apply this on techniques, applications such as scikit-learn, they take that into account for you. They just calculate what is the rank of the matrix and they use the smaller dimension.
You're saying that you either have to have a small number of data or small parameters?
Yes. You want to use the smaller of the two. Yes. Thank you. Okay, how do we actually do this? So we'll walk through this in the hands-on session, but let's just take a step through the code snippet. So the first thing that you would do is you would import the PCA application. You define, in this case, this is using a randomized PCA, which is a faster algorithm, but only computes the first handful of eigenvectors. You would select the number of components you want to output, in this case 5. You want to calculate the mean spectrum. We would generate the principal component analysis or instantiate the PCA application. We would fit it to the spectra, and then we'd output the principal components themselves. And we'll walk through exactly these steps in the hands-on. When you do this, you go from a set of input spectra, generate the eigenspectra themselves. So each one of these input spectra can be reproduced by a linear combination of the eigencomponents. The second aspect that's associated with this is the eigenvalue. The eigenvalue effectively tells you the amount of variance within the system that's contained with each one of those components. And so if we sum up the eigenvalues, we can see that after the first 10 eigenvalues, we're containing 95 or 94% of the variance of the whole system. So that means that if I just projected each one of these spectra down onto the first 10 eigenvectors, I can reproduce the variance of the whole system to within 95%. Why is that useful? Well, that's useful because this provides you effectively with a compression. Right? If you go from 4,000 spectral elements down to 10 components, then you've got a compression of a factor of 400. This shows you a set of spectra. The black line, the red line is the input spectrum, and the black line is the reconstructed spectrum using the eigenvectors, using just the first 10 components. So you can see that you can reproduce the input spectrum to a high degree of accuracy. If you were just looking at the continuum, you only need about 3 to 5 components. If you actually want to get the line ratios correct within the individual spectra, you need between 10 and 15 components. And we'll talk about why that's the case in a few minutes. So that's nice, right? It gives you a compression. What that means is I can take any spectrum and now describe it as just 10 components. And that's it's useful in model fitting, as we'll look later on. It's useful in representing data, because if I can represent any spectrum with just 10 numbers, it gives me, I can store those 10 numbers within a database and reconstruct any input spectrum. But the interesting aspect about it is really that the amplitudes that we multiply each one of the eigenvectors by to reconstruct a spectrum are actually correlated with physics. So this plot shows you the correlation or the distribution of effectively the first 2 coefficients for the principal component analysis. This is a distribution of 400,000 points from the Sloan Digital Sky Survey, Spectra. And then what we can do is we can look at each one of these regions within this scatter plot. If you look at galaxies within this region, they all have elliptical spectra. If you look at galaxies within this region, they all have spiral spectra. If you look at galaxies in this region, they all look extremely strange and unusual, and usually are junk. And we'll come back to that right at the end of the class. So we have a technique that gives you the ability to compress. We have a technique where the coefficients themselves correlate physically with the properties of the data. So this, moving from elliptical through to spirals, what this trajectory is really telling you is the star formation rate within that spectrum. So you can now describe the star formation rate within a galaxy using, in this case, just 2 components. So that's quite a powerful technique. But there are problems with principal component analysis. And one of the principal problems is that some aspects of the data are nonlinear. PCA is a linear process. You're effectively just rotating those axes to align with the maximum variance. But if I looked at a series of spectra, and if I looked at, say, a quasar spectrum, then there's a large or strong variation, a large amount of variation in the actual line width of that spectrum. So if I took one individual emission line and I looked at those emission lines over a range of different quasars, I would see that the width of that emission line actually varies dramatically. And in fact, the shape of the emission line would vary as well. And that's hard to reproduce with a set of linear functions. So if you took a Gaussian and you changed the width of that Gaussian, and then you tried to reconstruct it with just a handful of linear components, you need many components to describe the variation in the line width. And so you see that when you're looking at data from the Sloan survey. So if you take galaxies which principally have fairly narrow line widths, you can describe the galaxy spectrum with about 11 components. If you take quasars with extremely broad lines, then you need between 20 and 30 components. So it's not as compact as you would actually like. So let's start talking about a couple of other techniques that you can think about that may be more compact, give you better compression for nonlinear features. And one of these techniques is independent component analysis. It's a linear process. But independent component analysis comes from, I think it originally came from signal processing and electrical engineering. And the idea behind it is often referred to as the cocktail party problem. So the problem that you're trying to address is, imagine that you're in a room. And imagine that there are 3 speakers within that room, all talking away. And then you have 3 microphones spread out within the room. Then each one of those microphones is going to be picking up some linear combination of all the speakers. And what you want to be able to see, so X here corresponds to a microphone, S corresponds to a speaker, and A corresponds to the amount of that speaker that this microphone is picking up. Right? So here we have 3 microphones, each picking up a different combination of each one of the speakers. So you can see it's a linear problem. And what we really want to be able to do is to understand what is the mixing of these components, or more importantly, can I calculate a matrix that unmixes? So I can actually take the input from the microphones, unmix it, and recover the underlying speakers. Right? So the basis behind independent component analysis is the idea of statistical independence. And the simple way to think about this is, just from the central limit theorem, as I add in random independent vectors, that as I add more and more random independent vectors, the distribution I'm going to look at is going to become more and more Gaussian. Okay? So if adding together random independent vectors produces a Gaussian distribution, if I want to create components that are not random, that are not independent, I want to look for as non-Gaussian a signal as possible. Okay? And so what I'm going to do is to try and take these data and look for non-Gaussianity. So try to produce a series of signals, right? So the voices from the 3 people in my room, I want to maximize the non-Gaussianity of those distributions. And non-Gaussianity is either described in terms of the kurtosis, or in terms of the entropy, or in terms of usually the negative neg entropy. So how do I actually do this? Well, if I do this independent component analysis, again, it's relatively straightforward. The classic technique for this is called fast ICA. And fast ICA uses, I believe it's using kurtosis. So I define, again, the number of components that I'm interested in. I create the, basically, I apply the independent component analysis to the actual spectra, and then I output, and again, we'll go through this in hands-on, we output the resulting independent components. So what does this actually look like? Well, this shows you the principal component analysis for a set of input spectra, plus the independent component analysis. You can see the first component in each one of these is the mean. We subtract the mean before we do principal component analysis. We subtract the mean before we do independent component analysis. And there's 2 things that you can see from here. One is that they basically are finding the same signal, right? Even though this is looking for linear combinations that maximize the variance, and this is looking for components that have as maximum non-Gaussianity, okay? You still pull out the same structure. You're pulling out the same information, okay? You're just ordering them in different ways. So the first component on the ICA corresponds to the, it's related to the second component on the principal component analysis. You can see that the continuum between the two is very similar. The difference between independent component analysis and principal component analysis is that with independent component analysis, you tend to do a better job in terms of isolating the individual emission lines. They tend to pull out much easier. It's easier to pull those out from the actual continuum than from a PCA, where PCA tends to mix both the line emission and the continuum emission. But each one of those techniques, they have their, and I'll show some examples for the independent component analysis. But they're basically pulling out the same amount of information. And this makes sense, right? Both independent component analysis and principal component analysis are linear. They're assuming that the spectrum is made up of a linear sum of components. And that makes sense from a physical point of view. And this comes back to what I was saying at the beginning. You have to think about it from the physical model as well as from the statistical model. And that is, if I take an individual spectrum, then I can describe that spectrum in a very kind of a simplified form as the summation of different populations of stars. Right? So being able to take that spectrum and decompose it into a linear combination of basis functions makes sense. Right? So the statistical technique that we're applying, both with independent component analysis and principal component analysis, seems appropriate from a physical sense for the data that we're applying it to. Non-negative matrix factorization, NMF, is just you can think about it as looking for bases that are non-negative, right? And that also makes sense because we know that you don't subtract. When I'm building up a spectrum of a galaxy, I'm adding components to it. I'm adding stellar populations into it. And so we won't have time to kind of go through that, but it's worthwhile actually considering that approach. And there's some fairly fast applications for that. So we've looked at two things. We looked at principal component analysis, and we've looked at independent component analysis. The underlying principles behind both of those is that I can describe any spectrum as a linear summation of components. Let's take a slightly different direction and think about what can we understand or what can we extract from the data if we're looking at local structure. And this is often referred to as manifold learning. And the classic example for manifold learning is this diagram up here, is the S-curve, or sometimes this is done as a kind of a Swiss roll. And the idea here is, if I look at this data, this three-dimensional distribution of points, you can immediately look at that data and say, it's clearly a two-dimensional space or two-dimensional manifold within a three-dimensional space. Right? I should be able to take these data and just unravel it onto a plane. And if I do that, then the data themselves will actually, the colors of the points will actually correlate as a position along that plane. Right? So I should be able to take these data here and just unravel this S, and then I will go from blue all the way through to red. Data that are clustered up here will be clustered in this two-dimensional projection. And the question is, how do I go from this three-dimensional space and project it down onto this two-dimensional space? Well, from everything we've heard so far, you would say, well, the first thing I'm going to do is I'm going to apply principal component analysis to this, and I'm going to look at what the directions correspond to. Well, if I take principal component analysis, it would see this as a three-dimensional distribution. Right? I would get principal axes. My principal axis will go across here. The second axis will probably go up here, and the third axis go through here. So if I now said I'm going to project down onto the first two of those components, I get a plot that looks like this. So what I'm actually end up doing is I'm mixing these different components. You can see that the red and the green are actually being mixed up here. So what can we do about this? Well, what we can do is we can look at local structure within the data. And this is where manifold learning comes in. Manifold learning is trying to learn the underlying structure, this S shape, before we project it down onto a low dimensional space. And the basics behind this is, if I find a point within this space, if I look at all of its local neighbors, I can calculate what are the weights of its neighbors that will reproduce the position of that point. Once I've calculated those weights, I can say I'm going to fix those weights, and now I'm going to project this data down into a lower dimensional space such that I preserve those weights. So what that means is that when I project it down, sources that are close in the three-dimensional space are going to be close in my lower dimensional space. And if I do this for this S shape, what I get out is a figure that looks like this. Right? So we take each point, we look at its nearest neighbors, we calculate what are the weights of its neighbors that will reproduce that input point, and then fixing those weights, I calculate where would I project that point down to in a lower dimensional space such that I maintain these weights. And this ends up effectively doing solving two sets of linear equations. Okay. So let's just talk about, I'll show you some examples of this in a second, but let's just talk about what are the challenges associated with this. Because we said that what was the issue with PCA? PCA was trying to reproduce nonlinear structure through combinations of linear components. Well, what's the challenge associated with manifold learning? Well, clearly there's a few points. One is that if I take this point here and I say I'm just going to take the three nearest neighbors, then I'm going to get the three nearest neighbors are going to be fairly local. Right? And so I'm going to use a very local set of points to reproduce what the position of that input point, my test point. If I said I'm going to use 1,000 or 100,000 nearest neighbors, then I'm going to use all of these data to try and reproduce the position of that point. And you can see now that if I start looking for nearest neighbors that cross between this region here and this region down here, this is going to bias. I'm not going to get the right manifold, right? So I'm sensitive to the number of nearest neighbors I'm working with. I'm sensitive to the distance that I'm prepared to go out to when I'm calculating those nearest neighbors. And if I'm sensitive to that, then I'm also going to be sensitive to outliers. If I have an outlier up here, and I'm including it in my number of nearest neighbors, that's going to bias the manifold that I actually learn. Okay? So you have to be careful about outliers. You have to be careful about the number of nearest neighbors. And there is no prescription out there that tells you exactly how many numbers of nearest neighbors you're going to have, and there's no prescription out there that tells you the dimensionality of the data you have to project it down to. There's not the equivalent of the eigenvalues that you get with principal component analysis that tells you that the first 5 components will reproduce the 90% of the variance of the system. Right. So you have to be more careful about how you choose the dimensionality of the data, because you're setting the dimensionality and you're projecting the data down into that dimensionality. Okay. But in reality, it's also, the other aspect about it is it's relatively slow. You have to find all of the nearest neighbors, and then you have to effectively do 2 sets of eigenvector or SVD analyses on a couple of large matrices. And we'll go through this again in the hands-on. But it works pretty well. So you have to be careful about outliers. You have to be careful about the number of spectra that you're using to train your data. But when you apply this, this is just showing you for the Sloan spectra that we did the PCA for. This is now just looking at 2 components. Okay, the first and the third component coming out of LLE. The points correspond to the distribution of the coefficients or the values of the axes from LLE. What's interesting here is that the input data themselves are galaxies and quasars. So you remember I said for PCA to describe a galaxy spectrum, a quiescent galaxy spectrum with just the continuum, you needed 5 components. To describe the line emission, you needed around 11 to 15 components. To describe quasars, you needed 20 to 30 components. So that would say that if I did a principal component analysis and I want to separate the data, I'd have to project it down onto 30 odd, maybe 40 components. And so that's not that lower dimensionality when you're trying to work with the data. This is just projecting the data down onto 2 components using local linear embedding. The colors of the points correspond to the types of galaxies. So blue corresponds to quiescent. So if I march across here from the bottom left up to here, and I look at the average galaxy spectrum within each one of these boxes, I go from an elliptical to a spiral. So it's separating out the ellipticals through to the spirals in the same way that the principal component analysis did. If I zoom out this plot, it looks like this. And if I walk along this locus up here, what this is going from is narrow line to broad line quasars. Okay? If I move across here, I go from line-emitting galaxies of different line widths and different amplitudes. So you can see that the quasars and the quiescent galaxies and the line-emitting galaxies and the transient population that go from broad line to star-forming galaxies are all described in a two-dimensional plot. They all separate out. So this is telling us that the data themselves, in terms of this question of how do you actually classify galaxies, can be done in a two-dimensional space, not the 4,000 dimensional space that we measured the data in. Right? And so that's important because it says two things. One is when I'm just doing a local linear embedding on the actual spectra themselves. I'm not pre-processing, I'm not measuring line widths, I'm not measuring emission line strengths. I'm just taking the data and projecting it down onto this low-dimensional space, and I'm getting a classification straight out of it. Right. So this suggests that we need to think about both linear and nonlinear applications when we're trying to do classification. What local linear embedding does not give you, which principal component analysis and independent component analysis do, is it does not give you a set of coefficients from which I can reconstruct a spectrum. For me to reconstruct the spectrum in this region here, I have to take all of the input galaxies, or QSOs, and just average them. Right? So it doesn't give me the compression in the sense of being able to give you 4 numbers and you being able to draw what the spectrum actually looks like. Right? So there are pros and cons to both of these things. This shows you a comparison, and this is where we're going to get to when we do the hands-on. This shows you a comparison of principal component analysis applied to quasars, absorption line, and emission line galaxies. Blue are quiescent galaxies, red are broad line quasars, green are emission line, and this shows you the equivalent for LLE. This is a slightly different data set. You can see with principal component analysis just using the first 3 components, so 1, 2, and 3, there's a lot of mixing. When we actually do LLE, these different populations separate out. So use the right tool for the application that you're working with. In the same way with when you're working with simulations, it should be the question that you're asking that should define the simulation that you're using. It should be the question you're asking with the data that defines the application that you're applying to the data. So what can we actually do with these sorts of techniques? Well, if I can compress the data, then it makes it easy for me to fit models. Right? And if it's easy for me to fit models, I can also look at data and say, when does that data not fit the model? And this goes back to what we started with, where we talked about anomaly finding in terms of a machine learning type application. So this is an input spectrum from the Sloan. The input spectrum itself is given by the black line, so that's the original spectrum. If I can describe any galaxy spectrum by just, say, 4 or 5 components, or say 11 components if I want to get the emission lines as well, then if I want to do a regression model, all I'm doing is I'm regressing and I'm solving for the 11 coefficients that go into that, or the 11 coefficients that multiplied by these basis functions would reproduce the input spectrum. So I can just solve for these coefficients just doing a standard linear fit or least squares fit. Then I can start looking at the residuals. So if I take this spectrum and I fit using my eigenvectors, if I fit the eigenvectors, I get the blue line. These are just doing a least squares fit to the eigenvectors themselves. If I take this fitted spectrum and I subtract it from the original spectrum, I get this. Okay. Now if I overlay on that residual spectrum a template model, and that model is for a type 1a supernovae, you can see what I'm actually doing is I'm extracting out in these residuals, I'm actually finding a supernova spectrum within the SDSS spectra itself. So I'm subtracting out the underlying host galaxy spectrum. I'm looking at the residuals. Those residuals correspond to a supernova. I'm actually cheating a little bit here, because when I'm cheating, I'm actually fitting the supernova at the same time. So I'm jointly fitting both the coefficients for the galaxy plus a range of different models for the supernovae. But the reason I can do this fast is I'm only searching over about 11 separate parameters. Right? In fact, what I'm really doing is I'm searching over one set of parameters which correspond to the time of the different supernovae, and then I'm just regressing for the coefficients that correspond to the eigenvectors for the galaxy, and I'm regressing for the actual amplitude of that of the actual supernovae. But this means that it's extremely fast, rather than just trying to generally fit a range of, say, Brusewell and Charlot models plus a range of supernovae. But it really is cheating because I know what the anomaly really looks like. I'm searching for a known source within SDSS spectra. The technique itself works reasonably well. You have to be careful about poor fits to the data. You have to do filtering. Effectively, what you have to do is you have to come up with a classification scheme that allows for the likelihood of the fit and the amplitude of the supernovae. But if you do that, you can come up with a relatively good population of supernovae spectra measured from the supernovae detected in SDSS spectra in a way that is completely serendipitous. Right? So this was not what the SDSS was designed for, but you can find these unusual spectra. Okay. And then you can use that and you can calculate supernova rates. And in principle, these supernova rates are complementary to the image-based supernova rates, because effectively what we're looking at are spectra in the cores of galaxies, because each one of the fibers is centered on an individual galaxy, and we're looking at the central 3 arcseconds of that galaxy. Okay. So I said that was easy, and that was easy because what I'm really doing is I'm just fitting models that I know about. What happens when I'm looking for things that are unusual and I don't know what it looks like? Right? Well, in this case, what I can start to do is to look for outliers. Right? So whether I'm doing principal component analysis, or whether I'm doing independent component analysis, or whether I'm doing local linear embedding, I can plot up the coefficients, and then I can look for points that are significantly further away from this locus. And this is for a set of stars. And for this set of stars, again, these are Sloan spectra. Each one of the points in each color is a star that has been classified by Simbad. Okay, so we know from people looking at the individual spectra what these stars correspond to. And what we immediately see is we get a basic locus for the distribution of the points, and then we can start identifying where the outliers are. And if we start looking at these outliers, we find that these outliers up here correspond to H2 regions in nearby galaxies. So the star was actually misclassified. It's actually a part of a nearby galaxy that was classified by the image analysis, the photometric pipeline for SDSS, as a star. They put a fiber on it to measure the spectrum, but the spectrum itself is not consistent with it being a stellar source. And so this immediately pulls out a set of outliers. The spectra look like this. You can see there's strong emission lines, and that tells you why they don't fit the kind of general locus of stars. So we can exclude those. The second set of outliers we have down here correspond to cataclysmic variables, and they also correspond to some forms of white dwarfs. But this shows you the cataclysmic variable stars. And again, because they have strong emission lines, this draws them away from this central locus. So this gives you an idea that the way you can interact with data is by looking for the outliers. You can identify unusual populations. And the next thing you want to do is to do this in an iterative sense, where I've identified these outliers, I can exclude them, and then I can progressively start narrowing in on this stellar population itself. And so once I've got rid of the cataclysmic variables and I've got rid of the H2 regions, I rerun my local linear embedding, and then I look for the next set of outliers, and the next set of outliers themselves correspond to carbon stars. So this is this hierarchy of classification that you need to take, which always involves you actually looking at the data and analyzing it. Okay. So I'll go through just fairly quickly on the last couple of points, because I want to get into the hands-on, and I want to be able to kind of go through using a lot of the Python code. So how can I actually do this in a rigorous manner? Right? From a statistical or a machine learning application, what I'm doing is I'm looking for robust, low-rank detection of outliers. Right? So one way of thinking about this is, imagine that I took an individual spectrum and I tried to recover it or reproduce that spectrum with one component. I can calculate what the residuals are. And then I can try and reproduce it with 2 components, and then 3 components, and 4 components. And what I can do is I can sum up all of the residuals of how well it gets reproduced with 1, with 2, with 3, with 4, with 5, and so on. And this allows me to assign a probability of how easy it is to reconstruct that spectrum. Okay? And if I do this, I can order all of my spectra. I can produce a rank-ordered list of all of the spectra based on how easy it is to reconstruct them. And once I've got that rank-ordered list of spectra, then I can say this is the most unusual spectrum, as in it's the hardest one to reproduce. This is the easiest one that I can reproduce. And so to work with these data at that stage is you have to start analyzing them visually, and you have to start classifying them. And this is where you have to bring in kind of the physics, not just the machine learning application. So if you do this, you can produce much like Galaxy Zoo, which you heard about earlier in the week. But instead of doing this for Galaxy Zoo for individual images or Galaxy Zoo for the general population, what you want to do is to do this as Galaxy Zoo for expert classifiers, or scientist zoo, I guess, in some way. And in this case, what we're doing is we're rank ordering all of the input spectra, and we're saying this is the most unusual spectrum. So why don't you look at this input spectrum and classify it, and then tell me what it is. And if it is, if it's real, then it's a discovery. If it's junk in the data, then we'll move on. Okay? And this is what you get if you go through this. The first classification, if using local linear embedding, the most unusual spectrum in the SDSS is this planetary nebula here. It's a little bit hard to see the lines. If you were a planetary nebula person, you would say that doesn't actually look much like a planetary nebula to me in terms of the spectral lines, because some of the emission lines are actually missing. And the issue with this is that what's happened is that the SDSS analysis pipeline has detected an emission line that is so strong that it saturates the detector, and the analysis pipeline has said, well, that's clearly a problem with the detector, and it's masked out that region, and then it interpolates across that region. And so it masks out a lot of the flux from that spectral line. So in reality, this is anomalous. Sorry. This is anomalous for 2 reasons. One is because it's a planetary nebula. There are only about 3 planetary nebulae in this sample, this 50,000 stellar spectra that go into this sample. But it's also anomalous because something has gone wrong with the spectral reduction, and therefore there's a problem with actual data analysis. And so the first pass through, that whenever you analyze these data, the first pass through is you always come out with junk, right? You always come out with problems with your data reduction. And it's usually, from our kind of rule of thumb, it's about the 3rd time through. So you find junk, you mask out the junk, you run your analysis again, you find more junk, you mask out the junk. And then by about the 3rd time, you start pulling out astrophysically interesting objects. And these are the sorts of objects that you get out. This is a cataclysmic variable, which is 2, in this case it's 2 orbiting white dwarfs. this is, I think there's only one of these in the sample that we found. This is a white dwarf with a debris, of which there are only 3 known in the SDSS. The way these techniques or these objects were found in the SDSS was someone went in and looked at every single stellar spectrum from the Sloan survey. So there's a few 100,000 of those, but it was spread out over 10 years. So if you sit there, each time you're having a cup of coffee and you decide you're just going to classify the unusual spectra, you can do that sort of process. But it's much better if you can use a machine learning type application to say, why don't you look at these 10 objects first, rather than looking at everything else, right? And that's the sort of thing that you can use these tools for. Okay. So I'm going to finish there, and then we're going to move over on to trying to reproduce all of the diagrams and figures that I've gone through in this section. So we'll go through principal component analysis, we'll go through independent component analysis, we'll go through local linear embedding, and we'll see how we can identify anomalies within those data. So before we move directly on, I think we'll take a 5-minute break just so you can stretch your legs. Has anyone had problems with installing AstroML on their machines? No one? Do you want to raise your hand? Or for scikit-learn? Any problems with scikit-learn? One, okay. Before we kind of go into this kind of hands-on session, if you go to this website here, which is www.astro.washington.edu/users/ajc/HIPACC, all in capital, you'll find there's 2 files. There's a text file, which is tutorial, and there's a Python file called lle-funct.py. If you can download those both into your directories, the tutorial is just going to go through all of the commands that we're going through here. And the reason for that is so that you don't have to type everything in. We will type most of it in, but just so you have everything in one place. And the func lle.py is just a couple of functions that would be incredibly tedious to type in that we'll just import as we go through. If you're having problems with scikit-learn and installing that, you can log on to Gordon with your account, and if you just source this path here, that will set up everything for you, and you can just you can follow along, and we can do the hands-on tutorial with you running on Gordon as opposed to your laptop. Okay? So that is source twiddle ux455151/astroml.setup. And everything should work for you. Okay. So, any questions about anything we've talked about so far? Yeah.
You talked a lot about going back to the fundamental physics when these coefficients derived from PCA. Have you done that same thing for supernovae or other types of spectra? Like to understand physical parameters?
So we've been wanting to do that with the supernovae. The problem is that the supernova component assumes that we know what there's a coupling between what you fit for the model for the galaxy and the model you fit for the supernovae. One thing we were trying to do was to go back to all of the objects that we detected supernovae, take another spectrum of them, subtract that spectrum from the input from the first spectrum where we detected a supernova, and that gives us a direct measure of because in principle there'll be no variability in the actual galaxy. Unfortunately, by the time we decided to do that, Sloan had moved from SDSS 1 to SDSS 3, and the spectrograph's completely different, and it's much harder to work with the data, to actually match those 2 spectra and subtract them. So we haven't actually done that. Other anomalies. Again, it's the coupling between the model that you're fitting and the structure in the anomaly. So if you actually had better spectral models or a better way to constrain the parameters of the input galaxy spectrum, then it will be a nice technique to work with. Okay? So let's just take a 5-minute break. allow you to download the tutorial, and then we'll walk through all of the various steps that we're going to go through.